Alright, so we're going to finish up our sound notes right now and take what we have learned about how waves interact with each other and apply sound to how all that works. So we talked before about how reflection is when a wave hits a barrier that it can't pass through, so it bounces back. So an example of how sound is reflected is mainly through the term echo, which I know you've heard before. So an echo is many reflected sounds, and a lot of times you can hear this if you're in a room that doesn't have any furniture. You can hear the sounds bouncing off the walls, or you might be able to hear your voice if you scream off the top of a mountain. Diffraction, we've said before that that's the bending of sound waves around the edge of a barrier. So we've said before that you don't necessarily have to be standing in the doorway of our classroom for someone to be able to hear us. They might be able to stand outside of the doorway or down the hall, and they could still hear what's going on in our room because the sound waves bend around the edges of the walls. Finally, sound applied to refraction means that the speed of sound waves actually can change based on the medium that they're traveling through, because the molecules are spaced differently between solids and liquids and gases. So for in this picture we have a lightning bolt striking the ground, and so it actually adds on to the sound that you hear because the sound travels faster through the ground than it does in the air. Now, we don't have this on the slide because I moved this slide over to our wave behavior notes, but we said before that resonance is the reason that glass could shatter as a result of certain sounds. So when certain frequencies add up to the natural frequency of glass, for instance, it makes the amplitude add on, and this is a type of constructive interference. So constructive interference is when two waves combine and they make a louder sound. And so we can see this in these two pictures where these waves actually match up perfectly with crests and troughs, and so they combine into what you hear, which is a loud sound. And remember, destructive interference is kind of the opposite, when the waves kind of cancel each other out, so they could combine and make a softer sound, or in some cases they could actually cancel out sound. So if any of you have the headphones or earphones that are noise reducing, that means that it kind of muffles out all the other sound around it, and that means that the frequency of the vibrating molecules that make up the headphones will help to buffer any sound that's trying to pass through them, which means that it ends up canceling out. Now, you may have heard of the Doppler effect before, and this is the change in frequency of a sound as the source of the sound moves in relation to the listener. So, for example, if you've ever been standing on the side of the road, say you're waiting for the bus to come and cars drive by you, you've probably noticed that the sound of the car seems to get a higher and higher note as it comes up towards you, and then as soon as it goes by, the note goes down. So if you watch racing, or if you've ever been around like a police car when it has its siren on, the reason that the sound seems to change as it goes towards you and then away from you is because the sound waves that are going out are pushed together at the front of the car as it's approaching you. And so when it's pushed together here, you end up having a smaller wavelength as they're being smushed here. And when we have a small wavelength, the frequency is higher. That means that the note goes up. And on the other side, you can see that the waves here are spread out further, which means you have a longer wavelength and a lower frequency, so the sound goes down. So other ways that we use sound, you've probably heard the word ultrasound before. The word, or the prefix ultra, means higher, and then sonic means sound. So these are sounds that are above what we can hear. Humans can only hear a certain amount of frequencies, and there are some sounds above our frequency that we can't hear, such as like a dog whistle, sonar, and things that are used in medicine, like when a woman is pregnant, you can use ultrasound waves to kind of bounce back off of the baby and get an image of what the baby looks like, even though it's still in the womb. You can also find different like blood clots by using ultrasound waves also. The word infrasonic literally means below human hearing. There are some animals that use both ultra and infrasonic sounds in order to communicate. So elephants are examples of animals that use really low sounds that are below what we can hear. And sometimes we can hear what they're kind of saying to each other, but a lot of times they communicate with sounds that are below what we can hear too. And you've also probably heard the word echolocation. And again, this is a compound word. You see the word echo here. And so basically animals are using echoes of these ultrasonic or infrasonic sounds to find food. They send out a sound, and when it bounces off of these objects like an animal or a tree, they're able to figure out kind of an image of what the world looks like around them, which is pretty cool. So if you have any questions about how sound works and how we can relate these applications of sound, then please write those questions down and bring those to class tomorrow, and we'll work on this a little more in class before we have a quiz on it. You have a good afternoon.